Cool. Well, thank you, Jung-hee, and thanks to the workshop organizers for this wonderful opportunity. It's a pleasure to be here speaking about lattice-based cryptography. Lattices are a really wonderful mathematical object which have a number of surprising applications in mathematics, in number theory, algebraic number theory, and in computer science. Today we will focus on applications of lattices in cryptography, where it has been used both to break crypto systems as well as to construct crypto systems. We will the goal of this series of talks is to give an overview of the various uses of lattices in cryptography. And if I understand right, this will be in 5 lectures, 2 today and 3 tomorrow. Okay, so without further ado, let's get straight to business. Okay, what are lattices? Well, how do you construct a lattice, right? So let's look at 2-dimensional space. This green point there is the origin, 0, 0. Right? I pick 2 linearly independent vectors, integer vectors, integer coordinates. Call it b1 and b2. b1 is 2 minus 2 here, and b2 is 3 minus 1. And I construct all linear combinations of b1 and b2 with integer coefficients. Okay, so b1 plus b2 is a vector in the lattice. So is b2 minus 2b1. So the coefficients can be positive or negative, but they're integers. b2 minus b1. So much fun. Let's keep going. And what you get is a sort of a periodic grid of points. And this is the lattice generated by b1 and b2. Okay. So this is this is a nice picture. In fact, what I will do for the series of talks is I will start with pictures, and then I will show some pretty pictures, and then I'll move on to the whiteboard to do some algebra. Okay. This is a lattice. It's a lattice in 2 dimensions. How do you write it down? What is a more algebraic way of writing it down? Right. The lattice generated by b1 and b2 is a set of all linear combinations x1 times b1 plus x2 times b2, where x1 and x2 are integers. The same thing that I said in words. Okay, so why 2 dimensions? I'm restricted to 2 dimensions because that's all I can draw in PowerPoint. In fact, you can generalize this to m dimensions, any m that you want. And the lattice generated by m vectors b1 up to bm is simply the set of all integer linear combinations of these m vectors, m linearly independent vectors. Okay, it's a very sort of a natural object. But why, what are these lattices good for? I mean, this is nice, right? I mean, it's a simple object, but what is it good for? Lattices in computer science have really been a Swiss Army knife. I mean, it has been used all over the place. It's been used in algorithms. In fact, the best known integer programming algorithms use lattice reduction, lattice technology. Integer programming, remember, is an NP-complete problem. Right, so it's hard to solve in polynomial time, but the best known algorithms, exponential time algorithms, but the best known algorithms use lattices. Factoring polynomials over the rationals. Factoring polynomials over finite fields is supposed to be easy. Over the rationals, the best algorithm known uses lattices again. In fact, this is an algorithm discovered by Lenstra and Lowash, that's the LLL. And it's really the application that started off the use of lattices in computer science. Finding small roots to polynomial equations. You have a univariate polynomial equation which is guaranteed to have a very small root. Can you find it? Right? And this is a technique, this can actually be done using lattices again, and this is a technique due to Coppersmith. Okay? Many algorithms. I'm not going to mention the applications in number theory, but lattices are not an object in computer science. It was actually sort of discovered by number theorists. And over there, you have again a number of surprising applications of lattices, including a proof of quadratic reciprocity, proof of what's called Lagrange's 4 squares theorem. Any number can be written as a sum of 4 squares, right? What is a proof? Proof is based on lattices. Okay. Hopefully, I'll show this. It's a very cute proof. I can't help showing it over here. So hopefully, I'll show it at the end of this lecture. Okay. So that's algorithms. Complexity theory. Okay. lattices are very rich in the sense that they have a connection between their worst case complexity and the average case complexity. Okay, not many problems have this kind of nice behavior. Lattice problems are rich in the sense that they give us a hierarchy of problems between P and NP, belonging to different complexity classes. So that's complexity theory. And finally, the topic of this series of lectures is cryptography. Okay. What about cryptography? Cryptography, lattices have been so-called a double-edged sword, right? I mean, they have been used both in breaking crypto systems and in constructing crypto systems. And in fact, the first sort of set of applications of lattices back in the 1980s was in actually breaking the Merkle-Hellman crypto system, knapsack, and low-density subset sum-based systems, and so forth. Later, it was used to break, low exponent RSA. It was used to show how to factor a product of two primes, given a small number of bits of either of the prime factors. So factoring is supposed to be a hard problem, right? Given n equals p times q, product of two primes, it's hard to factor. But using lattices, what you can do is if I give you a small number of bits of either of the factors, you can actually compute the entire factor. This is amazing, an amazing application of lattices that you can do. That again can be used to sort of break crypto systems. And then, in the mid-1990s, people realized that lattices are useful not just as a destructive tool, not just in breaking crypto systems, but actually in constructing cryptographic schemes. So one-way functions, starting from the seminal work of Aita in 1996, he started off this constructive use of lattices in cryptography. Public encryption, the first scheme was due to Aita work, and the Bregev, and a whole bunch of works along these lines. Identity-based encryption, and more recently, even fully homomorphic encryption scheme. Fully homomorphic encryption scheme is really the holy grail of cryptography. It's an encryption scheme that allows you to compute functions inside the encrypted data. Okay, I give you an encryption. You can't see what's inside it because it's a secure encryption, right? But you can compute arbitrary functions inside the encrypted data. Okay, so this is the kind of magic you can do with lattices, and I will actually describe a new construction of fully homomorphic encryption in a couple of days in my talk on Thursday. Okay, so as you can see, lattices are extremely versatile in computer science, especially in cryptography. Well, that's great. That's wonderful. Let me tell you a number of more reasons why you should consider the study of lattices in cryptography. Okay. Number one is that traditional crypto systems based on number theory, based on factoring, based on discrete log, are all susceptible to quantum attacks. So if you had a quantum computer, then using Shor's algorithm, using various other algorithms, you can break all these systems. You can break all the factoring and discrete log-based systems. But lattices, no. Okay, so far, we don't have any way of breaking lattice-based systems using quantum attacks. In fact, as far as we know, quantum algorithms don't do any better than classical algorithms when it comes to lattice problems. Okay, so a quantum resistant. That's the nice thing about that. Lattice-based crypto systems have very simple, very efficient operations. The operations are just adding and multiplying small numbers. The basic operations are just addition and multiplication. What I would call grandma safety, which is, what did your grandma tell you, right? I mean, you shouldn't put all your eggs in the same basket. It's good advice in general in life, good advice in cryptography also. Okay, so what if, number theory-based crypto systems fail? Okay, you need an alternative to base cryptography on. That is lattices. And finally, and perhaps the most important point, which I already said, but it bears repeating, is that lattices can actually be used to construct very powerful cryptographic primitives. Things that we don't know how to construct based on number theory. Factoring, we don't know how to construct fully homomorphic encryption. Discrete log, no clue. But lattices give you this powerful primitive. Okay, so these are all the myriad reasons why you should be interested in considering studying lattice-based cryptography. Okay, so that's it. Enough selling. Hopefully, you guys bought my motivation to study lattices. what I will do in this lecture, we'll have 5 lectures. In the first lecture, which is like right now, I will tell you a little bit about the basics of lattices. What are lattices? What kind of objects, what kind of problems are we interested in studying on lattices? I will tell you about a very important theorem on lattices called Minkowski's theorem. And I'll tell you, a very important sort of problem, a central problem in the study of lattices, namely the shortest vector problem. In fact, let me say that all the lectures will be organized around a central theme, right? So, each lecture will have, a theorem or an algorithm that I will describe, and everything that I develop in the lecture will be sort of geared towards that end. Okay. So, first lecture we'll do Minkowski's theorem after doing some basics. The second lecture will consider algorithms for the shortest vector problem, namely the LLL, the celebrated, Lenstra and Lavosh algorithm called the LLL. So that's all, lattices in computer science and algorithms. Okay. Tomorrow we'll delve into lattices in cryptography, in constructing crypto systems. First, in the first lecture tomorrow, I'll describe 2 problems called SIS, called short integer solutions. That's SIS, and LWE, so learning with errors. That's LWE. And these problems can actually be used to construct one-way functions, collision-resistant functions, in a very natural and very simple way. Okay? So by mini-crypt, I mean one-way functions, things which don't have trapdoors, right? I mean, one-way functions, collision-resistant functions, they are mini-crypt. Okay? The next lecture, I'll go to the public key vault. I'll describe a public key encryption based on the learning with error problem. And finally, we will finish up with sort of a notion of trapdoors for lattices, a very natural notion of trapdoors for lattices. And I'll show how to construct a chosen ciphertext secure encryption scheme based on these trapdoors. Okay, so that's the plan. Again, if I'm going too slow or too fast, if I'm writing too small in the board or too large, please feel free to interrupt. Please feel free to ask questions. Questions are always welcome. Okay, so that's the plan. And with that, okay, good. So before getting into the lecture, let me tell you that I'm going to take my material from a couple of different sources. There's the book that Daniele Micancio and Shafiq Al-Basr wrote on complexity of lattice problems. I'm going to take sort of the basic material from this book, and a couple of lecture notes of what Dragiv and Daniele Micancio in their course notes, and I'm going to sort of liberally use material from there. Okay, so these are the references. I will actually, hopefully, I'll put this PowerPoint slides will actually be available later, so you can look at the references later. Okay, so that's the material I'll use for the lectures. Okay, so with that, let's get to lattices again. Okay, so lattices again, 2 basis vectors, all linear combinations. I get a lattice, right? So the basis is represented I can represent the basis as a matrix. The first column is the first basis vector. The second column is the second basis vector. So I'm going to represent it sort of column by column. Okay. And now this is all sort of integer combinations of v1 and v2, which I can write as a matrix vector product. Okay. So it's a lattice. You look at this definition, you say, this looks familiar, right? This notion actually looks familiar. Why does it look familiar? Because there is a very related notion of sort of vector spaces over the reals, right? So what is a vector space? You have 2 basis vectors. You take all sort of linear combinations of these 2 basis vectors with real coefficients. Okay, this is a vector space over the reals. In fact, if I do that with the 2 vectors that I wrote down on the board, you will get the entire plane, entire 2-dimensional plane. Okay. The difference between that and lattices is that in lattices, I only allow you to take integer linear combinations of the basis vectors, which will give you sort of a discrete set as opposed to sort of a continuous space. Okay. It's good to remember. These 2 are related, but there's a very important difference between them. Okay, so lattices, great. Let me ask you a question. What is the lattice? So this is a basis, okay? Two vectors, 14, 12, and 167, 143. Okay? So it's a weird basis, right? What is the lattice generated by this basis? Can anyone tell me? Take a pick. Take a guess. Don't be afraid. What could this lattice be? I take all integer, positive and negative integer linear combinations of these two vectors, these two columns. What do I get? Pictorially, what do I get? Have you seen this before in this talk? Well, no guesses, no takers. Well, it turns out to be the same lattice. Okay, so you go through the effort of drawing up all linear combinations of integer linear combinations of these two base vectors. Voila, you get the same lattice. Okay. A little more sane example. Okay, so here is another basis for the same lattice. 3 minus 1 and 5 minus 1. If you take all linear combinations, again you get the same lattice. Okay, so that's nice. In fact, a lattice has infinitely many bases, not just 1, 2, and 3, but really infinitely many bases. Right, so that sounds weird. How do I tell if I give you two bases? Okay, this 1, 1, 2, 0, this nice basis, and this weird basis with like large numbers. How do you tell if these two lattices, these two bases generate the same lattice? Is there an efficient way? Is there a computationally efficient way to do this? Well, turns out yes. Most problems that I'll talk about in these lectures are hard problems. They're not easy to solve. But for a change, this one is actually an easy problem. Okay. So how do you? And the important component in sort of deciding if two bases generate the same lattice is a lemma, which says that a lattice generated by B and B prime are equivalent. They are the same sort of set, same grid, if and only if there exists a matrix U such that B prime can be written as B times U. And what is this matrix? It's a very special matrix called a unimodular matrix. Okay, what is a unimodular matrix? Unimodular matrix is a matrix with integer entries. Okay, so all integer entries, whose determinant, the regular sort of determinant, is a plus or minus 1. Okay, the absolute value of the determinant is 1. Okay, so if there is such a matrix, such that B prime equals B times U, then these two bases generate the same lattice. On the contrary, if there doesn't exist such a matrix U, then these two bases generate different lattices. Okay, so that's a nice characterization, right? So how do you use this to decide if two bases generate the same lattice? Compute B prime times B inverse times B prime. Okay, that's a matrix U, right? That I can do because B and B prime are full rank matrices. They're M linearly independent vectors, therefore a full rank matrix. Compute the matrix U and compute the determinant. Is the determinant 1 or not? Okay, determinant is 1, they generate the same lattice, and if it is integer entries, then determinant 1 will generate the same lattice, otherwise not. Okay. Okay. How do you prove this? How do you prove this lemma? Okay. So let's see how to prove this. Okay. For this, I need to use the board. Now comes the hard part. Okay. So how many of you cannot see it? Well, let me start writing down things. Okay, so all right, so what do we want to prove? This is a strange marker. You see how tech savvy I am. You see how tech savvy cryptographer I am. Let me speak for myself. Okay. All right. So what do we want to prove? Lemma. Two bases, B and B prime, generate the same lattice if and only if there exists a unimodular U such that B prime equals B times U. Okay, now how many of you can see it? Cannot see it. I think you should move on. Let me try to write a little bit bigger. Okay, so how do you prove it? So this is an if and only if statement. Let me show both directions. Okay, suppose, let me show you the easy direction first. Suppose B prime equals B times U. Okay, for a unimodular matrix U, I want to show that the lattice generated by B is equal to the lattice generated by B prime. Okay, that's what I want to show, one direction. So how do I show this? Well, let's look at this basis. It has many vectors, right? M vectors, M columns. And this can be written as B times some unimodular matrix. Okay? So what does this say? This says that every vector bi prime, v1 prime in particular, can be written as a linear combination, integer linear combination of the vectors b1 up to bm, right? So if you take this matrix multiplied by u1, you get b1 prime, which is a integer linear combination of b1 up to bm. So what does this say? It says that b1 prime is in the lattice generated by b, right? b2 prime, the same argument, is in the lattice generated by b, and so forth. So all these vectors bi prime are in the lattice generated by b. In other words, the lattice generated by these vectors, B prime, is a subset of the lattice generated by B. Right? All the vectors bi prime are in this lattice, and therefore all its linear combinations are also in this lattice, and therefore. Okay, so that's great. What do I need to show that two sets are the same? I need to show that the first set is a subset of the second set is a subset of the first. Right? I showed one of these statements. So let me actually write down B in terms of B prime, right? So B equals B prime times U inverse. I didn't do anything. I just the main observation now is that if U is a unimodular matrix, its inverse is also a unimodular matrix. Okay? Because how do you compute the inverse of a matrix? You take various minors, right, and then divide it by the determinant of U. Right? All these minors are integers because they are determinants of various submatrices, and the determinant of U is 1. Okay, so what you get, U inverse is an integer matrix whose determinant is 1 over the determinant of U, which is plus minus 1. Okay? So if U is a unimodular matrix, U inverse is also a unimodular matrix. Write down this. Do the same argument for this relation. Okay? So when you do this, you will see that L of B is a subset of L of B prime. Put these two things together, these lattices are really the same. Okay? So that's one direction. I showed that if B prime is B times U for a unimodular U, then the lattices are really the same. Okay? Questions? Feel free to ask. Okay, so let me erase that, and let me show you the other direction. Okay, what do I want to show? If suppose the two lattices are the same, okay, then I want to show that B equals B prime U for a unimodular U. Okay, so that's what I want to show. Well, how do you show this? Well, suppose that the two lattices are the same. What does this mean? I can write all the vectors in B prime, B1 prime up to Bm prime, as a integer linear combination of the vectors in B. Right? So I can write it as B times U, where U is an integer matrix. Right? This is by definition of lattices. Well, I can do the same thing the other way around, right? I can write B as also an integer linear combination of B prime using a different matrix, U prime, which is also an integer matrix. Okay, so I have these two relations. So let me put them together and write B prime as B prime, U prime, U, right? So I just replace B by B prime, U prime here, and this is also an integer matrix. Okay, all I need to show now is that this matrix has determinant plus minus 1. Then I am done. Right? How do I show this? Well, let me take the determinant of both sides. Okay? So I take determinant of B prime. I get the determinant of B prime, U prime, U. Right? Same thing. And determinant is multiplicative. So determinant of the product of two matrices is a product of the determinants. So I get determinant of B prime, determinant of U prime, and times the determinant of U. Okay? Now, determinant of B prime is non-zero. Okay, so I can cancel that out, right? So this goes away, and this goes away. Get 1 here. Now I get determinant of U times determinant of U prime is 1. Okay? Now what is the determinant of U? U is an integer matrix, right? So its determinant has to be an integer, right? And so with same is the case with U prime. So you have two integers whose product is 1. Okay? What can these integers be? If you have two integers whose product is 1, then both the integers are plus 1 or both the integers are minus 1. Okay? So therefore you get the determinant of U is plus minus 1, and the same with determinant of U prime. There you go. What I just showed you is you can write B prime as B times U, where U is an integer matrix whose determinant is 1. And therefore it's a unimodular matrix. Okay? So that's the proof of this theorem. And what it shows you, it's sort of a constructor proof, right? What it shows you is an algorithm to test if two bases generate the same lattice. Given two bases, you can easily tell if they generate the same lattice. Right? So that's what this theorem shows you. Okay, so that's my little tryst with the board. All right. So this is an easy problem. Yes.
How do you know that
How do I know the determinant of B prime and determinant of
because of that?
yes, but okay. This is B prime. So this is determinant of B prime. I didn't do anything funny, right? Determinant of B prime, determinant of B prime. I just cancel that, right? And I can do that as long as it's not 0, right? So, that's great. Okay, so, all right, so that was a nice little lemma. Okay, so far we defined a lattice in terms of a basis, right? We said take two basis vectors, take all linear integer combinations, you get a lattice, right? Is that the only way to describe this lattice? Okay, so this is the same lattice as before, except that I removed the basis vectors and I marked up a bunch of more points. Okay, can you think of another way to describe this lattice? Another sort of basis independent way to describe this lattice? Guess? This is a little bit of a harder question. Let me tell you the answer. This lattice is in fact the set of all integer vectors, pairs of numbers, such that the sum of the two numbers is even. Okay? Look at 2, 0. 2 plus 0 is even. 1 minus 1. 1 plus minus 1 is even. Okay? If you look at any such point, any point in the lattice, you will see. In fact, this is in the set of all integer points whose sum is even. Sum of the two coordinates is even. Okay? This is a sort of a nicer way to describe a lattice, other than pick two basis vectors and all linear combinations. Okay? In fact, there is a sort of a generic way to describe lattices, a generic definition of lattices, which doesn't talk about bases at all, which is that a lattice is any discrete additive subgroup of Rm, R to the power m. R is real numbers, R to the power m is sort of the m-dimensional space. Okay. What does it mean? Discrete means that two lattice points cannot be too close. Okay. There is a minimum distance between any two lattice points. In other words, there is an epsilon bigger than 0, such that for any two lattice points, the distance between them is at least epsilon. That's what discrete means. Additive subgroup, the usual thing. If two vectors are in the lattice, their sum is also in the lattice. The difference is also in the lattice. Okay, so this is an alternate definition of the lattice, which doesn't talk about any basis at all. Okay, and it turns out that these two definitions are in fact equivalent, in the sense that for any lattice, for any discrete additive subgroup of Rm, there is a basis which generates this as a lattice, and the other way around. For any sort of lattice defined by basis, it is in fact a discrete and additive. It's additive, that's obvious. It's also discrete, which is also fairly obvious. So the two definitions are equivalent. In fact, if the two definitions are not equivalent, that would be a huge injustice. It's a huge mathematical injustice, right? I mean, so these two definitions are in fact the same. Okay, that's great. Okay, so that. Okay, so one more thing before we actually get into sort of interesting stuff, which is the notion of a fundamental parallelepiped of a lattice. Okay, so what is it? It is, in fact, the region enclosed by a fundamental parallelepiped of a basis is a region enclosed by the two basis vectors. Okay, this is the little parallelogram that B1 and B2 enclose, and that is a fundamental parallelepiped. Okay. How do you algebraically define the parallelepiped? It's a set of all linear combinations of B1 and B2 with coefficients between 0 and 1. Right? So the half open interval 0, 1. Okay, pictorially it looks like this rectangle, or this parallelogram. And observe, it's important that fundamental parallelepiped does not contain any lattice points. Although, when I draw the picture, it looks like it contains, all the 4 points in the square. It doesn't, because you have a half open interval. The only lattice point that it contains is, in fact, a 0 lattice point. Okay, so that's a nice little property. Unlike a lattice, parallelepiped depends on the particular basis you're talking about. So, this sort of other basis of the lattice has a different parallelepiped. Okay, so every basis has a different parallelepiped associated with it. But the nice thing is that, that sounds kind of terrible, right? Because the lattice can have infinitely many bases. So, should I talk about, which parallelepiped should I be talking about, right? That's really terrible. The nice thing is that all of these parallelepipeds have the same volume, have the same area. Okay, so it's not very obvious. I mean, so for this basis, it's actually obvious. So consider this basis and sort of the other basis that we drew before. I mean, they are kind of reflections of each other on the x-axis, right? So obviously they have the same area. But consider a different basis with really long, really terrible vectors, right? Why should it have the same area as this basis? It's not obvious, right? But it is true. And in fact, I'll tell you why it is true. But before that, let me define this quantity called the determinant of a lattice, which is the volume of the area of the fundamental parallelepiped. In 2 dimensions is the area, m dimensions is the volume of the fundamental parallelepiped. Okay. So let's sort of build some intuition for why all the different bases should have the same area, should have the same determinant, right? Let's look at this picture. What is the area of the parallelepiped? This is something we learn in like 4th grade or 5th grade, or maybe even like the 1st grade in Korea, I don't know. The volume of the parallelepiped is the base times the height. Okay, and that's 2 times 1 is 2 here. Now let me compute the determinant of this basis matrix 1, 1, 2, 0. Right? What do you get? The determinant is minus 2. In fact, the absolute value is 2. Okay? So the determinant is equal to the volume of the parallelepiped. In fact, if you take any other basis, let's say 3, 5, minus 1, minus 1, 3, 1, 3 minus 1, 5, 5 minus 1, compute the determinant, I get the same number. This other like monstrous basis, compute the determinant, How many of you are like human calculators? Can you compute the determinant of this? You compute it, you get the same number, 2. Okay. In fact, this is not surprising, given what we discussed so far. Remember our characterization of equivalent basis, right? So B and B prime are equivalent. If B, I can write B prime as B times U for a unimodular U. Okay. What that says is that determinant of B prime is equal to the determinant of B times the determinant of U is equal to the determinant of B, because U is unimodular. That's determinant 1, plus minus 1. Right? So in fact, what this says is that any two bases that generate the same lattice have the same determinant. Different parallelepipeds, but the same area, the same determinant. Okay. So that's the determinant of the lattice. The bottom line is that the determinant of the lattice is the volume of the fundamental parallelepiped, which can be computed as the determinant of the matrix B, the basis matrix. Okay. So with that said, let me go to the whiteboard. In fact, the rest of this lecture and the next lecture will be on the whiteboard. So should we sort of take off the projection, or should we leave it there? Leave there? Okay. All right. Okay. So we're building up towards the climax, right? Okay. All right. I promise you, I am going to define just one more notion, and we'll get to Minkowski's theorem. Okay. What is the last notion that I want to define? It's the notion of successive minima of lattices. Successive minima of lattices. Okay. What is a successive minimum? Well, so before I do this, I want to define the L2 norm, or the Euclidean norm of vector. The Euclidean norm of vector is nothing but its length in space, right? So I denote this as x2, or so the x with 2 lengths. This is the sum of xi squared. So let's say x is a vector of consisting of components x1 up to xm. This is just the sum of square root of the sum squared, right? This is this thing that we are all familiar with. So what is the successive minimum of a lattice? I want to define the notion of the shortest vector of a lattice. A lattice has many vectors. I'm interested in the shortest vector in the lattice. Can any of you tell me, what is the shortest vector in any lattice? Say that again? 0. Okay, there you go. 0. But it's a rather uninteresting shortest vector, right? So what I'm interested in is the shortest non-zero vector. Okay? Let me call that. Let me call the length of such a vector lambda 1. Lambda 1 of the lattice. Okay? Definition. Lambda 1 of the lattice is the minimum r bigger than 0, such that there exists a v in the lattice, non-zero v, whose length is equal to r. Okay? In plain words, it is the length of the shortest vector in the lattice. Okay, so I want to sort of put up the example again. It's good that we have. Okay, so can anyone tell me what's the shortest vector in this lattice? 1, 1, whose length is square root 2. Okay, so L2 norm is square root 2. There you go. Okay, so I'm not happy with just the shortest vector. I'm not happy at all. What I want to do is extend this to talking about the second shortest vector, the third shortest vector, so on and so forth. Okay, so how do I define the second shortest vector of the lattice? Any ideas? What is the obvious definition? The first shortest vector is a vector which has the minimum length. What is the second shortest vector? The vector that has the second largest length, non-zero vector which has the second largest length, right? This is the obvious definition. It's not a very interesting definition. Okay, so to see this, consider the following lattice. Okay, this is the origin, and I have this is the first basis vector. Let's call it maybe it's 1 0, right? And you have a bunch of points. The second basis the second basis vector is I don't know what it is, 0 maybe 10 to the 200. Okay, just because I can, right? So it's a huge vector. Okay? So what is the shortest vector? 1 0, right? What is the second shortest vector? 2 0. That doesn't sound very interesting, right? And third shortest vector is 3 0 and 4 0. It doesn't sound very interesting. What I want to say, how I want to define the second shortest vector is that it's a vector that is linearly independent of the shortest vector, which has the minimal length. Okay, so in this picture, this is my shortest vector, and this is my second shortest vector because it's linearly independent from the shortest vector. Okay, so in other words, I want to define the second successive minimum to be the minimum are bigger than 0, such that there exist two vectors v1 and v2 in L of B, both non-zero, which are linearly independent. Linearly independent is a very important condition, such that the length of vi is at most r. Okay, so what is the minimum length? Such that you have two vectors, two linearly independent vectors of length at most r. It's plain, simple as that. I mean, the definition looks complicated, but what it says is intuitively very simple. And I can, so much fun, right? I mean, 1, 2, I can keep going. I can do lambda m of L by the same token. Right? So minimum length such that there are m linearly dependent vectors of length at most r. Can I do lambda m plus 1 of L? I mean, does it make sense? It doesn't make sense because you have an m-dimensional space. You can only have m linearly independent vectors. So you have lambda 1 of lambda m of L. Okay. So a question.
So minimum was that or
The minimum length.
minimum length? So
Yes.
R in the case lambda 1 L is the minimum value of R.
Minimum r. Exactly. Thank you. Absolutely right. Minimum value of r such that there is a vector short. Exactly. So it's a number. It's not a set or it's not a vector. It's a number. Thank you. Okay. So given a basis, it's a question. Is there always a vector of length lambda 1 of L? Okay. So lambda 1 is the length of the shortest vector. Given a basis, is there always such a vector? Well, yes, by definition, always. Right? Is there always, given a lattice, is there always a basis consisting of m vectors, each of whose length is lambda 1, lambda 2, lambda 3, up to lambda n? That's another question that you might want to ask. Guesses? Yes, no, coin flip? So, question is this. Given a lattice, can I always find the basis of this lattice whose vectors have lengths lambda 1, the shortest length, lambda 2, lambda 3, up to lambda n? Right? Guesses? It could go either way at this point, but the answer is no. So it's actually quite surprising that you can't necessarily find a basis whose vectors have length lambda 1 up to lambda m. In fact, now that we have a dispute between me and Jamhi, let me show you a counterexample. Okay, so consider really the same lattice extended to n dimensions. Okay, so no, actually, let me correct this. So consider the lattice, which is the set of all x1 up to xm, such that all the xi's are even, or all the xi's are odd. Okay, so this is a set. Why is it a lattice? because it's discrete, because all the vectors are integers, the distance between any two vectors is at least 1, so it's discrete. It's additively closed. Why? Because if I take two vectors, all of whose coordinates are either even or odd, you will get another vector, all of whose coordinates are either even or odd, depends, but they'll have the same parity. Okay, so this is a lattice, and I want to claim that it doesn't have a basis whose lengths are lambda 1, lambda 2 to lambda n. So let's see what does this lattice look like here, right? So in 2 dimensions, the lattice has vectors, 0, 2, 0, 0, 2. Both are in the lattice because both the coordinates have the same parity. And it also has a vector 1, 1. Okay? And in fact, these vectors, 0, 2 and 1, 1 actually generate the whole lattice. Let's generalize this to n dimensions. You have one, the all ones vector. So the 2, 0, all zeros vector, the 0, 2, all zeros vector, and so on and so forth. You have m such vectors. Okay? Can people? Can I write bigger? I have this disease. I mean, I start writing and it becomes sort of smaller and smaller. It's sort of a monotonically decreasing function of time. So, thank you. Say that again. Oh, the font. Yeah, of course. Yeah, I'm gonna do that. Say that again. Okay, good. So the set is a set of all x1 up to xm, m-dimensional vectors, such that all the xi's are even, or all the xi's are odd. Okay. So 2, 0, 0, 0, 0, 0 is such a vector because all the coordinates are even. And the all ones vector is also such a vector because all the coordinates are odd. Right, so these are both vectors. In fact, all such vectors, generate the lattice. Okay. So why is this lattice so special? Why does it provide a counterexample to Jungi? Right? That's an interesting question. What is the minimum? What is the length of the shortest vector in this lattice? Okay. So I said that the lattice has vectors, 2, 0, 0, so forth, 0, 2, 0, so forth. Since I'm in 2 dimensions, I can only draw 2 vectors, but you can imagine, all these vectors. And then I have 1, 1, 1, 1. Okay. So what is the shortest vector? Assume that m is actually much bigger than, 5. Okay. M is bigger than 5. Then this is the shortest vector of the lattice. What is the second shortest vector? Well, this. What is the third shortest vector? Well, so all the vectors, 2 times the unit vectors, are in fact the m shortest vectors of the lattice. Okay? But if you just take these vectors, these m vectors, they cannot possibly generate the lattice. Why? Because the vector 1, 1, 1, 1, 1, I can never write it down as a sum of vectors of this form. Because if I take any sum of these vectors, they're always going to have even coordinates, and this has odd coordinates. So I can never write this vector as a linear combination of these vectors. In other words, the vectors 2 times the unit vectors, they form, a set of vectors with minimum lengths, but they can never be a basis of the lattice. Okay, so that is the counterexample. Okay, so this is just a curiosity, Okay, good. So now with that, let's get to the meat of the talk, which is Minkowski's theorem. Hopefully, I have time. This is the most non-trivial part of the lecture. Bringing the. Can you actually turn this off? Turn the light off. Because I'm not going to use the PowerPoint at all. I can move this. Thank you so much. Okay, now that we are over the big hurdle of the day, let's move on to Minkowski's theorem. And what this theorem asks is the following: okay, we have a lattice. We defined a notion of a shortest vector. The question is, how small, how short can the shortest vector be? Right? Can I put a bound on the length of the shortest vector? That's the question. The question is how short is lambda 1? How small is lambda 1 about? Right? And the intuition is that if you have a very dense lattice, okay, if you have a lattice whose points are all very closely packed together, lambda 1 is small. It's likely to be small, right? So what does it mean that the points are closely packed together? It means that the determinant of the lattice is small, okay? So the intuition is that the smaller the determinant of the lattice, the smaller the length of the shortest vector. Right? That's the intuition. What Minkowski's theorem does is it connects, it makes this intuition formal. Okay? So in other words, more formally, what Minkowski's theorem says, whether Minkowski is that the guy with the beard and the mustache that you might have seen in the first slide of my talk. In any case, I'll show him again tomorrow. So what does Minkowski's theorem say? It's a very beautiful theorem. There's many applications. Minkowski. It says that for every n-dimensional lattice L, lambda 1 of L, the length of the shortest vector, is at most square root m times the determinant of the lattice to the power 1 over n. Okay, that's what it says. So what it gives you is an upper bound on the length of the shortest vector. Okay? And it goes in the right direction because it says that if the determinant of the lattice is smaller, then lambda 1 is smaller, and so forth. Okay? So we'll get to why these terms are the way they are. Why the terms, this equation might look weird, right? Where does this come from? We'll see in a minute. Okay. Given this theorem, say that again. Okay, good. This is 1 over m. Okay, the mth root of determinant.
1 over
m. M is the dimension of the lattice. What I do is I take square root m times the determinant to the power 1 over m. So mth root of the determinant. Okay, so it's a natural question to ask, given this theorem, is this theorem tight? Right? Are there lattices? What does this theorem say about general lattices? Does it give you sort of a tight bound on the length of the shortest vector or not? Right? I mean, this is a natural question to ask. In fact, what it does is first sort of simple observation is that there are lattices for which Minkowski is not tight at all. What I mean is that the length predicted by Minkowski, the length of the shortest vector predicted by Minkowski, is a lot larger than the length of the actual shortest vector. There is a vector which is much, much smaller than the length predicted by Minkowski. Okay? So what is such a lattice? Well, our favorite lattice, which I erased from here, which is a lattice consisting of vectors, 1, 0, 2, 0, and so forth. And the second vector in the lattice is 0, 2 to the 100. Okay, this is a ridiculous lattice, right? What is the length of the shortest vector in the lattice? It is 1, right? It's exactly this vector. What does Minkowski say about this lattice? So it says that lambda 1 of L is at most square root of the dimension, which is 2, times the determinant of the lattice, which is the area of this parallelogram, right? So what is this area? It's 2 to the 100 to the power 1 over the dimension, 1 over 2. Okay, so this is root 2 times 2 to the 50, which is a ridiculous upper bound. Right? The actual shortest vector is 1, and yet Minkowski says 2 to the 50. Okay? So this bound can be very non-tight, depending on the particular lattice you're looking at. But the interesting thing is that there are lattices for which Minkowski is tight. For which Minkowski is tight. Okay, and this is not obvious. This is not something I'm going to present. In fact, lattices for which this bound is tight come from the study of sphere packings. How dense can you pack spheres such that there is very little space between them, so empty space between them, right? So it's a question of sphere packings, and there are lattices that come out of sphere packings, and they give you tight bounds for. They give you a lattice where Minkowski is actually tight. Okay, so the bottom line is that for some lattices, Minkowski bound can actually be very non-tight, but in general, there is a lattice for which it is actually tight. Okay, so that's the question of tightness of Minkowski. Let me say one more word about this bound, and then let's go to the proof of this theorem. Okay, so the one thing that actually bothers me when I see this bound is that I don't really understand why this determinant of L to the 1 over m term comes from. What is the intuitive explanation for this term? The idea is this. Okay, this term ensures that the bound scales appropriately. Okay? In other words, what I mean is that let's say you take a lattice which is the original lattice times 2. Okay, so you take each basis vector, multiply it by 2, and that gives you a new lattice. What is the determinant of this new lattice? It is 2 to the m times the determinant of the lattice, right? Because in each direction you scale it by a factor of 2. What is the lambda 1? What is the shortest vector in this new lattice? It is 2 times the shortest vector in the original lattice. Okay. So now you see why this determinant of L to the power 1 over m term is important. Because if I take this new determinant and take this to the power 1 over m, I get 2 times the determinant of the lattice to the 1 over m, and this is the same sort of scaling factor that you see in lambda 1 of L as well. So this term ensures that the bound scales appropriately. Okay. So this is just an intuitive explanation. I see this bound and I see why are these terms important, and this is why